Hello, this is the lecture for rational expressions. A rational expression is a fraction where both the numerator and the denominator are polynomials. There's a couple of examples here. 3x plus 2 divided by 2x minus 8. There's a binomial in the numerator, a binomial in the denominator. Another expression appears here, x plus 7 over x squared plus x minus 6. This rational expression has a binomial in the numerator and a trinomial in the denominator. So with rational expressions, since we have variables in the denominator, there's the possibility that that value of that denominator could end up being 0. And if that happens, we have an undefined expression. When we're dealing with functions, we do not want undefined values. We do not want we do not want to ever divide by 0. So for that reason, the domain is very important with rational expressions. We need to make sure that we exclude any values from the domain that result in a 0 denominator. All right. So if we look at these two examples here, and let's go ahead and make them a function. We'll say this first one is f of x. Okay, and it's equal to 3x plus 2 divided by 2x minus 8. Well, if this was a function, the domain here, we would assume it was all real numbers, but we have to be careful because we can never divide by 0. So we need to find which values we need to exclude from the domain, or which values that x can take on that would result in a 0 denominator. To do that, we'll set that denominator equal to 0. So we'll say 2x minus 8 equals 0, and we'll go ahead and solve for x. So we'll add 8 to both sides and then divide by 2. So we see that when x equals 4, the denominator is equal to 0. So that means when we're referring to the domain here, we want to make sure we say that x cannot equal 4, or in interval notation, we'll say, well, it's all the values from negative infinity all the way up until the value of 4. But we need to exclude 4, so we'll use that parenthesis. And then we'll say that that interval is in union with all the values after 4, all the way out to positive infinity. Right? If we were to graph this on the number line, right? If we were to graph this on the number line, we'd say, well, let's say if 4 is right here, then we would have to say we'd have that open circle right there at 4, but all the values greater than 4 and all the values less than 4 would be okay. Let's see that better. Okay, look at the second example. Let's say that that function is maybe called g of x, right? Well, the domain of this function would include anything that does not result in a 0 denominator. Or we want to find the excluded values. We want to find the values for x that make that denominator equal to 0. So we'll set that denominator equal to 0 and we'll solve. Now that's a quadratic expression, and that one does factor, so we'll go ahead and factor that. That'll factor into x plus 3 times x minus 2. Okay, we'll use the zero product principle to solve here. Either x plus 3, oops, that's an equal sign, equals 0, or x minus 2 equals 0. So if we subtract 3 from both sides, we see that x equals negative 3, or if we add 2 to both sides, we see that x equals 2. All right, so my excluded values here, the values I need to exclude from the domain, are going to be 2 and negative 3. When I specify that domain, I'm going to say x cannot equal negative 3 or x cannot equal 2, but in interval notation, This is how we commonly specify the domain of a function, right? In interval notation, this is going to be all the values from negative infinity up to -3 in union with all the values between -3 and 2 in union with all the values greater than 2 all the way up to infinity. Okay, on the number line, if we were graphing that, it would look like this. We'd say if, well, let's see, we'll say that -3 is here. We'll say that 2 is here. We want all the values smaller than -3, but not -3. We want all the values between -3 and 2, but not -2 or -3, and then all the values greater than 2. Okay, so let's talk now about simplifying rational expressions. Since rational expressions are really just fractions, right? They're really just fractions. We know that if we were to write the fraction 2/4, most of us would be pretty uncomfortable with that. That should be simplified, right? That fraction should be simplified. We know that that'll simplify to 1/2, but the reason that simplifies to 1/2 is because if we factor the numerator and the denominator, 2 doesn't factor, but 4 factors into 2 times 2, right? And then what we can do here is we can divide out a 2. There's a 2 in the numerator and in the denominator. When we divide them out, we're left with 1/2. Right? We're going to do the same exact thing with our rational expressions, right? Rational expressions are a little more complicated, but what we're going to do is factor both the numerator and the denominator and then just divide out any common factors. All right, so if we look at the first example over here, look, the first example, x squared plus 2x minus 8 over x squared plus 10x plus 24, that numerator will factor into x plus 4 times x minus 2. And that denominator, that's going to factor as well. That's going to factor into x plus 4 times x plus 6. Okay. Now that we've fully factored both the numerator and the denominator, we can see that there is a common factor of x plus 4 in both the numerator and the denominator. So they'll divide out, and the simplified version of this rational expression is x minus 2 over x plus 6. All right, look at the second example here. This rational expression has a binomial in the numerator and a trinomial in the denominator, but this binomial is a difference of squares, right? So it'll factor into x plus 1 times x minus 1, and that denominator will factor into x plus 1 times x plus 5. Okay, we can see we have a common factor between the numerator and the denominator. It's the x plus 1. They'll both divide out. So this expression, the simplified version of this expression is x minus 1 over x plus 5. Right? So simplifying rational expressions is we're going to do the same procedure that we would do to simplify a simple fraction. We're going to factor, but fully factor both the numerator and the denominator, and then just divide out any common factors. When we multiply rational expressions, that is also going to be the same procedure as when we multiply simple numerical fractions, right? If we were to multiply, maybe let's say we want to multiply 8/12 by 3/16. Okay, so most of us want to just go ahead and multiply the numerators and multiply the denominators, and we can go ahead and do that. 8 times 3 is 24, and 12 times 16 is 192. Okay, but then I have to reduce that fraction, right? I can't leave it like that. That's all weird. So to reduce that fraction, let's see. I want to look for common factors I can divide out. Well, let's see. 24 is 2 times 12, so I could say this is 2 times 12, and 192 is evenly divisible by 2. Let's see, 192 divided by 2 is 96. Okay, and then I can divide out those 2's, but I'm not done yet. I can factor some more out, right? 12 could be written as 4 times 3. I wonder if 4 evenly divides into 96. It does, it's 24. So I could do this. I could say 12 is 4 times 3, and 96 is 4 times 24, and I can divide out a 4. Okay, 3 over 24. Now, reduce any further? Well, 24 is 8 times 3, so I can go a little bit further with this even, right? I can say this is 3 over 3 times 8 and divide out my 3's. Okay, so that took a lot of work. It took a lot of work to simplify that 24 over 192 down to 1/8. I might, if I'd noticed right away that 24 was 8, or that not 192 is 8 times 24, I could have saved myself some steps. But it doesn't matter. I get to the result. I get to my end result eventually anyway, right? Well, if I take this approach when multiplying rational expressions, I can get myself in some trouble here. Because if I just start multiplying right away, if I multiply 2x squared minus 10x plus 12 times x squared minus 1, I'm going to have to multiply every term with every term, and I'm going to have a lengthy polynomial divided by a lengthy polynomial. And then how do I go about simplifying that? Whew, the factoring there is not going to be fun. So what's better is if I factor all the terms, if I completely factor all the numerators and all the denominators first, then divide out the common factors. And see, I could have done that up here as well. Look, with the numbers, if I completely factor that numerator and denominator, 8, well, that can be factored down to 2 times 2 times 2, right? And 12, well, that's 2 times 2 times 3, right? And 3/16, well, 3 doesn't factor, but 16 will factor down to 2 times 2 times 2 times 2, right? And then if I factored it first, if I fully factored it first, right? So in this case, I'm factoring the numbers all the way down to primes. If I fully factor them first, I can go ahead and divide out my common factors. There's 1, there's 1, oh, there's a 2 and a 2, and there's a 3 and a 3. And then all I have left, nothing in the numerator, so I'll leave a 1 there as a placeholder. 1 over 2 times 2, 1/8. And it gets me to the same result. Okay, so with rational expressions, I always want to factor first because factoring long polynomials is not something that we want to get involved with right now. It's very complicated. All right, so let's start with this example. Let's factor the first rational expression. I noticed that when I look at the numerator of that first rational expression, there's a greatest common factor. Let me pull that out first. There's a 2 is the greatest common factor between all those terms. So let me pull that 2 out, and I'm left with x squared minus 5x plus 6. Okay. I can also pull a 2 out down here in the denominator of that second rational expression. So let me do that. When I pull that 2 out, I'm left with x squared minus 4. All right, so that's only those 2 have greatest common factors. But can I factor further? Yes, I can. Yes, I can. Right now, if I wanted to, I could divide those 2's out. I could, or I could just wait as well. Maybe I'll just wait. Let's see if we can rewrite this. So this is now 2 times x squared minus 5x plus 6 over x squared minus 2x minus 3 times x squared minus 1 over 2 times x squared minus 4. All right, let's continue factoring here. I have this trinomial x squared minus 5x plus 6. That will factor. I can factor that into x minus 2 times x minus 3. All right, the denominator of that first rational expression will also factor. That's going to factor into x plus 1 times x minus 3. Okay, x squared minus 1 is difference of squares, so that'll factor into x plus 1 times x minus 1. Okay, the 2, well, that's not going to factor, but x squared minus 4 is another difference of squares, so that'll factor into x plus 2 times x minus 2. Okay, now my numerators and denominators are fully factored. I can go through and divide out common factors between the numerator and the denominator. There's that 2. I don't know why I crossed that 2 out. Just rewrite it. Yeah. So that 2, there's a 2 in the numerator and a 2 in the denominator. Those will divide out. Okay, there's an x minus 2 in the numerator here. There's 1 down here in the denominator. Those will divide out. There's an x minus 3 in the numerator and the denominator. There's an x plus 1 in both the numerator and the denominator. So what are we left with here? X minus 1 over x plus 2. Once we simplify the rational expression. Okay, multiplying rational expressions. When we divide rational expressions, we want to change the division into multiplication by using the reciprocal of the divisor and then go ahead and multiply. All right, so it's just like dividing simple numerical fractions. Say I want to divide 1/2 by 1/3, right? 1/2 divided by 1/3. Well, what I want to do is change this to a multiplication problem by using the reciprocal of the divisor. So this then becomes 1/2 times 3 over 1, or 3/2. Okay. Some of you may have learned some memory tricks in dividing fractions. You may have learned something like this: 1/2 divided by 1/3. You may have learned keep, change, flip. Keep the numerator, change that division to multiplication, and flip the denominator. That's all we're doing here. We're doing the same thing here when we're dividing our rational expressions. We want to change that division problem into multiplication by using the reciprocal of the divisor. Then we're going to go ahead and multiply. All right, so let's do that. Let's rewrite this as a multiplication problem. It's then going to become x squared minus 2x plus 1 over x cubed plus x multiplied by, and then we're going to flip that, right? Or we use the reciprocal, 3x squared plus 3 divided by x squared plus x minus 2. All right, so now we have a multiplication problem. We've got trinomials, but we want to fully factor and simplify before we do the multiplication, right? So the numerator of this first rational expression, x squared minus 2x plus 1, that is going to factor into x minus 1 times x minus 1. All right, x cubed plus x, well, I can pull an x out of there, right? It has a greatest common factor of x. So let's pull that x out. So x cubed plus x can be factored into x times x squared plus 1. The numerator of the second rational expression, looks like there's a greatest common factor of 3, so I can pull a 3 out. 3 times x squared plus 1. And this last denominator here, well, that'll factor into x plus 2 times x minus 1. All right, now that everything's factored, I can make this one big multiplication problem and divide out any common factors between the numerator and the denominator. So I see an x minus 1 in the numerator and the denominator. I see an x squared plus 1 in the numerator and the denominator. And it looks to me like that's all that we'll divide out. I've got to keep that x minus 1, the 3, the x, and the x plus 2. Okay, so we end up with 3 times x minus 1 over x times x plus 2. Okay. Now, I don't mind if you leave that in the factored form there. I think my open math accepts those answers, but if you wanted to pretty that up a little bit, you could redistribute and write this as 3x minus 1 over x squared plus 2x. Either one of those is perfectly fine. All right, when we add rational expressions, we have to establish a common denominator first, right? So if we wanted to add, say, let's see, say I wanted to add, well, I don't know, say I wanted to add 1/2 and 3/4. Okay, I can't add those until they have the same denominator, right? So I need to convert them to have somehow to have the same denominator. Well, what I normally do when adding fractions is I want to find the least common denominator. The least common denominator between 2 and 4 is going to be 4, right? And the reason for that is because when I fully factor those denominators, it becomes 1/2 plus 3/2 times 2. And my least common denominator here, in this case, is simply going to be the 2 times 2. To find the least common denominator, I want to go through and I want to find, I want to make sure all my factors are represented in the LCD. So my least common denominator is 2 times 2 or 4, right? So to establish the common denominator here, I'm going to have to multiply that 1/2. That 2 needs to be multiplied by a 2. So I'm going to need to multiply that 1/2 by 2/2. And then add to that the 3/4. So what I'm adding, 1 times 2 is 2, 2 times 2 is 4, so I'm adding 2/4 to 3/4. So my answer here is going to be 5/4. I want to do the same exact thing with rational expressions. I need to establish a common denominator before I can add them, right? But to establish this common denominator, I have to find the least common multiple of that common denominator so that I can do that. Now, in this case, they already have the same denominator, so I don't have to worry about the least common denominator. I can just add the numerator straight across in this first example. So this is then going to be 2x plus 7 plus x plus 8 over that same denominator, x squared plus 6x plus 5. And let me simplify that numerator a little bit. 2x plus x is 3x, and 7 plus 8 is 15. So 3x plus 15 over x squared plus 6x plus 5. Now I want to be careful here. This rational expression, I might be able to simplify it. If I can, I definitely want to do that. So let's factor the numerator and the denominator and see if it will simplify. I can pull a 3 out of both terms in the numerator, right? Got that greatest common factor of 3, so let's do that. When I factor out the 3, I'm left with x plus 5. When I factor that denominator, I have to do it underneath, so let's see. I can factor that denominator into x plus 1 times x plus 5, right? So now I can see, oh, it does simplify. Look at this. There's an x plus 5 in both the numerator and the denominator, so my final answer here should be 3 over x plus 1. I always want to make sure we simplify rational expressions. All right, so that had the same denominator. That wasn't that hard. We didn't have to do anything to convert the denominators. When we subtract rational expressions, if they have the same denominator, it's also not going to be too bad. We just want to subtract the numerators. The only thing tricky here is we have to be really careful that when we subtract a binomial, we subtract both terms of that binomial. So always use your parentheses here. I'm subtracting all of x minus 4. Always use your parentheses so you remember to distribute that negative. Okay, that's over x minus 2. Now, let me go ahead and distribute that negative. So this is in 4x minus 10 minus x. And then minus negative 4 makes that plus 4 over x minus 2. Okay, let's combine those like terms. 4x minus x is 3x, and negative 10 plus 4 is minus 6 over x minus 2. And let's see if that will simplify. Oh, there's a 3 that factors out of both terms of the numerator. So I could then write this as 3 times x minus 2 over x minus 2. And look at that, those x minus 2's are going to divide out. And my final answer here is simply 3. 3. Okay. So let's look at some examples now that don't have the same denominator. If they don't have the same denominator, we need to establish that first. And the way to do that is to find the least common denominator, and make that the denominator of all my terms. So let's practice finding the least common denominator first. All right, to find the least common denominator, we want to factor each denominator completely. And then we want to list all the factors of the first denominator and then add to that any factors of any other denominators that are missing. Okay? That final list is going to be that least common denominator. So let's see if we can find the least common denominator between 7 over 5x squared plus 15x and 9 over x squared plus 6x plus 9. All right, if I fully factor 5x squared plus 15x, let's see, I think the greatest common factor between those terms is 5x. So let's factor that out. And that leaves us with an x plus 3. It stays behind. Okay, so that first denominator will factor into 5x times x plus 3. The second denominator, that's going to factor into x plus 3 times x plus 3. Okay, so there's fully factored. Now let's list out all these factors and make the least common denominator. Our least common denominator here, we start, might as well start on the left. That first factor is 5x. Second factor is x plus 3. The next factor is x plus 3, but it's already there, so I don't need to add it. Oh, but there's 2 x plus 3's, and there's only 1 x plus 3 here, so I will need to add that second x plus 3. Right, so least common denominator is 5x times x plus 3 times x plus 3. Look at the second example here. Neither one of these denominators factors. That means my least common denominator here is going to have to be, it's going to have to be the first denominator times the second denominator, or 3x minus 2 times x plus 9. Okay. So finding your least common denominator. Now let's, after reviewing that, let's see if we can add 2 rational expressions that do not have the same denominator. All right, so let's start by factoring both denominators and finding the least common denominator. All right, that first one, x squared plus x minus 2, is going to factor into x plus 2 times x minus 1. Oops, I have to press you twice. Okay, and then x squared minus 1 is a difference of squares, so that'll factor into x plus 1 times x minus 1. All right, let's find our least common denominator. The least common denominator, first I've got the x plus 2 factor. It's the first one I see. There's an x minus 1, so let's add that. There's an x plus 1. I don't have that yet, so let's add that. There's one more x, there's an x minus 1, but I already have an x minus 1, so I do not need to add that one. Right? So there's my least common denominator. Now, what I want to do is I want to multiply each term by whatever is missing in that denominator, right? So that I'm establishing that least common denominator with both of those terms. All right, so let's just rewrite that because it's a little messy here. My first term is x plus 3 divided by x plus 2 times x minus 1. Okay, compare that to the least common denominator. It's missing the x plus 1. I need to add that in, or I need to multiply that. So I'm going to multiply this by x plus 1, but I don't want to change the value of that expression. So I need to multiply the numerator by x plus 1 as well. Right? Kind of just a fancy 1. That does not change the value here. Okay, but now, this is when we multiply rational expressions, of course, it's just like one big rational expression. So now my first term becomes x plus 3 times x plus 1 all over x plus 2 times x minus 1 times x plus 1. All right, now let's add to that the second term. The second term is 2 over, and in its factored form, that denominator is x plus 1 times x minus 1. Okay, compare that denominator to the LCD, the least common denominator, and I can see that there's an x plus 2 missing. So I need to multiply this one by x plus 2 over x plus 2. Okay. Now, both have the same denominator, so I can write them as one rational expression. X plus 3 times x plus 1 plus 2 times x plus 2 all over that least common denominator. X plus 2 times x minus 1 times x plus 1. Okay? And that's fine like that, but if you want to multiply it out, you can. You can. There isn't going to be any way to simplify this, but let's do it. We'll multiply it out just to make sure. X plus 3 times x plus 1 is x squared plus 3x plus another x, so plus 4x, and 3 times 1 is plus 3. Then plus, distribute that 2x plus 4, okay, all over. I'm not going to multiply those. I'm going to leave those factors as they are. X plus 2 times x minus 1 times x plus 1. All right, I can combine the like terms and pretty that up a little bit and write it as x squared plus 6x plus 7 over the x plus 2 times x minus 1 times x plus 1. All right. And then I could check to see if this factored and anything simplified, but I can tell you right now that when we're adding with having to establish a least common denominator, that they're not going to simplify. This doesn't even factor. X squared plus 6x plus 7 does not factor. Okay. Should we try one more? Let's try one more example when we're subtracting rational expressions. Actually, there's two on here, so we'll do them both. When we're subtracting rational expressions. All right, we need to establish the least common denominator. In this first example over here, the least common denominator, both denominators are prime. They can't be factored. So my least common denominator is going to be x minus 2 times x plus 1. All right, first rational expression is missing that x plus 1. So we'll multiply 2 over x minus 2 times x plus 1 over x plus 1. Okay, then minus my second expression, that denominator, the x plus 1 is there, but it's missing the x plus 2. So we'll multiply the 3 over x plus 1 by x minus 2 over x minus 2. Okay, now they have the common denominator. So I can combine them. I can say this is 2 times x plus 1 minus 3 times x minus 2 over x minus 2 times x plus 1. And I might simplify that a little bit. That numerator, I kind of want that to be a little bit prettier. So I'll distribute that 2. And I'll have 2x plus 2. Let me distribute that negative 3. So 2x plus 2 minus 3x, and negative 3 times negative 2 is positive 6 over the x minus 2 times x plus 1. And then I'll combine the like terms. See, 2x minus 3x is negative x. 2 plus 6 is positive 8, so negative x plus 8 over x minus 2 times x plus 1. And I'm going to keep that in this factored form. Okay. Nothing, when you're adding, subtracting, with denominators, they're not going to simplify. One more example here. These denominators do factor, so let's go ahead and do it. that first denominator factors into x plus 1 times x plus 5. The second one factors into x plus 5 times x minus 3. Okay, so my least common denominator here is going to be x plus 1, the first factor, times x plus 5, the second factor, times, oops, I already got that x plus 5, but I don't have an x minus 3. So times x minus 3. Okay, I'm going to need to, there's an x minus 3 missing in the first term, so I'll need to multiply that 1 over x plus 1 times x plus 5 by x minus 3 over x minus 3. Subtracted from that will be the 3 over x plus 5 times x minus 3, and that one's missing the x plus 1, so we'll have to multiply by x plus 1 over x plus 1. All right, now let's see, we can rewrite those. 1 times x minus 3 is just x minus 3. Let's go down here. X minus 3 over x plus 1 times x plus 5 times x minus 3. So that's x minus 3 minus 3 times x plus 1. Okay, let's see, we can simplify that. Let's distribute that negative 3. So we get x minus 3 minus 3x and minus 3 over the x plus 1 times x plus 5 times x minus 3. Okay, that's combining our like terms. X minus 3x would be negative 2x. Negative 3 minus another 3 would be minus 6 all over x plus 1 times x plus 5 times x minus 3. Oh boy, I'm out of room. Let's put another piece of paper up there. I can factor that numerator, but I won't be able to divide anything out because I can factor out a negative 2, but then I'm left with x plus 3, and this is an x minus 3, right? So it won't simplify. There's our final answer. And this concludes the lecture on rational expressions.